Okay, I think that we're ready. So shall we start? Okay, so let me briefly introduce the speaker of today. First, welcome all for our computational social science webinar. In this is in July. Okay, organized by the Computational Social Science Lab at the Chinese University of Hong Kong. As many of you probably know, that we normally invite speakers from outside, but today, we invite our own faculty members who is an expert in generative AI and social science research. So today we invited Professor Philip Zhang Renyu from our business school. He's definitely an expert in this area and also teaching related courses. He has an Xiaohongshu account. So he's famous there. Okay, I can't remember the name, but you can search probably using Zhang Renyu. Then you can search on Xiaohongshu, and you will know. He's very generous to share the syllabus of generative AI about for social science there, and also can answer your questions probably later. Without further ado, welcome Professor Zhang for the talk of today.
Okay.
Very much. Thank
Yeah.
you. Yeah.
Can everyone hear me and see the screen?
Yes.
Good.
Clear.
Okay. Thank you. So thanks for Professor Liang for the kind introduction, and thanks everyone for being here. I'm Renyu from CHK Business School. Broadly defined as computational social scientist, maybe. But anyway, today, hopefully I can share with you some of my recent endeavors and insights regarding the how to use generative AI for the simulation inference jobs in business research. Let me first give you some background why I work on this area. So there are two first principles I have in general in my research. The first one is that I hope this is my research could do something important. So AI is undoubtedly the most important topic of the humankind at this era. Second is that I should have some relative advantage. Basically, I don't have 10,000 GPU cards as OpenAI or Anthropic, so I cannot really do training. I cannot really do a lot of fancy stuff that I would like to do, unfortunately. So I will see, okay, what kind of things that I have as a business researcher. So what I will find is indeed simulation, as well as especially social simulation, as well as causal inference, which I believe most of computer scientists somehow ignore, but are also crucially important. Okay, to be more specific, I'm going to cover two topics today. The first one is how to leverage synthetic decision makers for social simulations, which means in general, in social science or business research, we need to derive some causality relationship between interventions and outcomes. The gold standard is, of course, randomized control trials, or sometimes we call it experiments or A/B testing in different contexts. However, such experiments are in general very expensive or ethically unacceptable if we do them on humans. However, generative AI provide us a new perspective and a tool to really simulate human behaviors through AI agents. Okay, so can we really use such synthetic agents for or to simulate some behaviors that of humans that could somehow respond to some interventions that could help us discover some causal relationships. That's a first topic I'm going to cover today. The second is that in a lot of cases, still we want to do causal inference or regardless what kind of statistical inference. However, we do not have sufficient labels that could help us do a valid inference with the necessary statistical property okay, such as root n square n consistency, so as we can construct the confidence interval and the central limit theorem, so on and so forth. However, generative AI provide us a way to scalably generate such low-cost labels. So like probably 10 years ago, we need to have human labelers to really give us these labels, which could be, again, expensive and sometimes unethical. But now, can we use generative AI to generate such labels at a low cost and at a scale? But for both topics, there is a central challenge that people have been observing and trying hard to really to solve them, which I call it that AI outputs or general AI outputs are often systematically biased, so that they somehow you cannot really you don't I should say it, you don't really know whether you can trust the results. Okay. Um, Okay, so basically, my talk today will provide some of my efforts, probably not really lessons, and lessons, okay, efforts and lessons along these two lines of research. Okay, okay, so at the core of both approaches is the idea of calibration. So by calibration, I actually mean that we have a large AI generated sample and a small human sample. So basically, the large AI generated sample has a lot of data, so that the variance is low, whereas a small human sample is it's unbiased. However, the variance may be large because of it by definition. I mean, because the sample size is small. If we have a really infinite amount of human sample, probably, I mean, yeah, the whole question is solved. On the other hand, if large language models could perfectly generate the outcomes very much similar or distribution-wise the same as human samples, the question is also resolved. So basically, it is precisely because of the drawbacks of both sides. Should we do a careful calibration task? So basically, the idea is like this. So I used Notebook LLM to generate this picture. Basically, so we have some uncalibrated LLM outputs generated by AI agents, and then we should do two things basically. The first is what I call it a pre-hoc behavioral engineering, which use some context engineering and harness approaches to somehow advise and discipline AI agents to produce human-like behaviors. Otherwise, it would just behave in essentially in an average fashion, like the entire human population, but not really exactly what you care about in this specific context and specific setting. Beyond that, what is equally important is what I call it a post-hoc debias for statistical inference. This is because regardless of how you context engineer or harness engineer your LLM agents to force it to produce something you like, there's still some gap between reality and AI generated samples. So we should do another round of post-hoc debias through calibration so that the statistical inference from the AI generated sample could be aligned with the human behaviors. Okay, or I should say could be aligned with the inference from human behaviors. Okay, so that's the high level idea. Okay, by the way, if you have any questions, probably you can just unmute yourself and ask during the talk. Yeah, or you can leave it to the end. Both are okay for me. Okay, so let me get started with the first part, that is the pre-hoc calibration to simulate human decisions at scale. Okay, so this is actually a very, I would say, a um, well-studied area, although not so many publications arise there, but a lot of people are trying this approach. That is to use LM as human surrogates for a lot of experiments. Indeed, last year at ICML, a position paper at ICML means that it's not really a research output or research technical research. Instead, it's some big shots like Eric Brunson from Stanford just argue that, oh, this is an important area, we should work on that, something like that. So basically, there's a ICML position paper uh, trying to advocate this area of research using LLM agents for social simulations. Basically, as you can see, this is of course fast scalable and cheap, and also it's making the research outputs reproducible. So following the same paradigm, another one use the same model, same context, same engineering techniques. They should produce similar results. Okay. And indeed, this is not just an academic endeavor. Industry people, or I should say the VCs or the markets also paying that. Here, I took a screenshot of a news from early this year, suggesting that Percy Liang from Stanford, who is famous for the Stanford Village, that simulation system, actually just brought this research idea into a digital twin startup with called I don't know how to call it, Smile, or whatever. Okay, and which raises 100 million US dollars, which I think is more than the total GenAI fundings that the CHK people can get in a single year. Okay, so basically it's a huge amount of money, and of course I think its market value should reach the unicorn, that means 1 billion US dollars reach. But anyway, so this is a important topic, yeah, both in terms of academic and in terms of the real market value, although it's still not a mature area of study, as I will show you later why this is challenging and how, yeah, I believe we can resolve such challenges. Okay, so the literature actually tells us that LLM agents could successfully replicate a lot of simple, well-structured tasks. For example, human-like fairness, reciprocity, risk preferences, that appear in a lot of games and real markets like dictator, trust game, utility management games, so on and so forth. So basically, a lot of paper document that LLM agents, when simply prompted, they could actually behave very similarly in these human behaviors, which are usually quite well structured and actually quite simple, but in the sense that the reasoning chain is straightforward. That said, there is also literature that documents LMs often fail in socially complex environments. So such environments usually involve multi-agents and all the agents that strategically behave in response to each other. Typical examples like public goods, prisoner's dilemma, 1120 money request game, and a lot of my area's papers in behavioral operations management. Okay, so yeah, in these replication efforts, the authors simply just document that, okay, yeah, the LMs could not, at least to the full extent, replicate what was documented in the original human study. So yeah, the basically the question emerges as why this is the case and how can we resolve such a challenge to so that LMs could really simulate the human behaviors reliably in socially complex environments. Okay, so that's two questions that I hope to articulate and address for the next probably 20 minutes or so. Okay, so the example or illustrating example, our starting point will be this management science paper 10 years ago by Kramer and Debel. So let me give you a very brief introduction of this paper. So basically, these two OM researcher, what they do is first they develop a behavioral queuing model. It's a simple economical or we should call it mathematical model. And with this model, So basically, you can think of it as I try to argue the point that Q has two, or weighting has two implications. The first implication is that congestion, which means you need to wait for a longer time to get your product or service. The second is the so-called signaling effect, which means if you know some of other consumers actually know the quality or value of this product, but you don't know, if you see a long queue, then probably you will infer that the quality of the product or service is good. So basically, the actual behavior of humans will depend on the trade-off and the entanglement of both forces. Okay, so that's the key point of this paper. And then they run a randomized experiment in the lab to test the two important hypotheses they developed through their theoretical model, which I will describe later. What are these two hypotheses? And then basically, and then they of course open source the data so that we can use it for calibration and a lot of other out of sample tests, so on and so forth. Another important reason I use this paper, the first is of course it's clear, it's transparent, and it's somehow not so trivial task for LLM. And plus, 3 years ago, there was a group of researchers who published a so-called replication study, which means they just run the same set of experiments, actually 10 experiments, and this paper is one of them, again, and in a different campus, I should say a different university. Usually, you know, these behavioral experiments are run in those behavioral labs in universities across United States of America. So they run such experiments again. That is a few years later, and then in a different university, the experimental results are consistent with original experiment. So suggesting that this behavior is not something that's really they fake it or it's just by chance. Instead, it's something that we could more or less reliably believe. And plus, there is another paper by a New Zealand researcher, Samuel Kirshner, who actually did the same thing as this management science replication paper, but using LLMs. And in his paper, he could not really replicate the result of this inferring quality from wait time because this is somehow not that straightforward from the AI agent perspective. The agent needs to do some reasoning to infer quality and so on and so forth. Basically, so as you can see here is the clear story. So we have a quite reliable human behavior well documented in the literature, and with also if we use LLM, use a simple idea, the most straightforward replication, then indeed we cannot really replicate human behaviors. So now there's the gap that, okay, can we really make it replicable using some systematic techniques, okay? Okay, so let me go in a little bit deeper into the context and the model. So basically, thinking of the two cases, the first case we call it Q00, which means in the market, every single consumer is unaware of the quality of the product, okay? So that basically means that everyone is just blind, just like let's say at CHK, a new restaurant opens, then of course nobody knows the quality. So basically, yeah, we cannot really infer the restaurant quality from the wait time. The next condition is Q50, which means in this setting, the half of the consumers are actually aware of the quality of this restaurant. So basically, if I'm a new consumer, I don't know the quality of this restaurant, but I see a line, then I could somehow infer probably there is indeed the quality of the product of the restaurant is probably good, okay? So that's the idea. So here's a pictorial illustration. So Q00 means nobody is informed. So here, a consumer comes in who is also not informed, then he may not purchase, then he will directly leave. He may purchase, and then she will join the the line, the waiting line, and the waiting line will be one more. Okay, W equals 2 then. Then in this case, if you are an informed consumer, basically you just you could you know the true quality. Then if the true quality is good, you will join. If it's not good, you will not join. If you are an uninformed consumer in this setting, then you will need to infer the true quality from the length of the wait line. Okay, so that's the idea. And basically, for the product value in the original paper, the high quality value is 3.5, whereas low quality value is 0. So basically, the ex-ante utility will be the reservation $4 plus the product value minus the wait time. That is $1 per unit time. Because in the original paper, it's 1 week. Okay, so basically we can theoretically derive, trust me, or you trust the original paper's authors, that we could derive these two hypotheses theoretically. The first one is that if we really observe, or a new consumer observes that waiting time is 0, then this uninformed consumer is less likely to purchase in the condition of Q50 than Q00. Basically, this means that some consumers are in the market. Some consumers are informed of the true quality of the product, but nobody joins. So this kind of, in this case, I will be more suspicious about the true quality of this new restaurant. So, and this is usually called empty restaurant syndrome in the literature. Okay, but this is not the only thing the paper tests, or we want to test with LLMs. The second hypothesis is that when the wait time increases, then in the case of Q0, Q50, which means that some consumers who are informed, in this case, there is trade-off, which means if we see a longer queue, of course, congestion matters. The quality inference also matters. So in this case, probably as a new uninformed consumer, I will still decrease my purchasing probability, but it's not as steep as in the case of Q00, where long waiting line only means longer waiting cost, which means the only thing that matters is congestion. Okay, so basically both effects somehow captures the quality signaling effect of waiting line. Okay. And as I said, so base hypothesis confirms with human data in this original paper, and 7 years later by the new replication study. So this is a kind of robust and somehow credible empirical results. Okay, so our framework looks like this. Hopefully, we're still working on it, but we have some promising results that I will share. So I'd also like to hear your opinion. Okay, so here's our idea. So the whole framework consists of 3 parts. The first part is, of course, the theory inputs, like what we have there. So my definition of theory means some low-dimensional representation of high-dimensional reality. So basically here, the core trade-off or the core theory here is that humans not only care about waiting costs, but also care about inferring quality from the waiting line. So basically, this is kind of the theory inputs that we would have. And of course, there's some other behavioral theory. I will describe later how we incorporate them in this framework. And within that, we would have 2 important components of engineering the system so as to make the replication possible. The first, I call it context formation. The core is that within any behaviorally important setting, so just like we live in this world, when we are facing with a decision, in this context, a lot of cases we need to, there's something matters, something that does not really matter. But as humans, we have a lot of quite personalized knowledge or a kind of some physical world knowledge that LLMs or AI agents are not aware of. So in this setting, we need to somehow provide the specific context representation for the AI agents. Okay, so actually, and um, only providing the correct context is not really enough. And the next part is, which I call it a kind of harness. So basically, within the same context, the same setting, different people may behave differently, or different people may navigate the context in different ways. So, for example, in this queuing game or queuing behavioral queuing setting, when you see a long queue, some people may really care about the quality, so they probably will care less about the long waiting time. Whereas some other people, like when you are in a rush, okay, you need to take a train or take a plane, then in this setting, probably don't really care that much about the signaling quality. You just want to go as fast as possible. So within the same context, people will think differently and make decisions differently. So basically, we need to that basically means that we need to fine tune the behavior, or we need to really parameterize such behaviors and really to learn the proportion of different type of consumers or different type of human agents in such settings. Okay. So indeed, by the way, the whole context also theory granted by the Nobel laureate Simon, actually, I think 50 years ago, sort of, they think humans' decision making also follows a similar paradigm to understand the context and then to really develop or navigate the context. Okay. And also, this is also very consistent with the engineering development of large language models. Like at the very beginning, so we just use a very simple prompt to ask AIs to do something, and later we know that context matters. So that's why we have the context engineering thing that last year or from starting from 2024. And then this year we have the new, I mean, open cloud code, codex, these things, they have very good harness. Okay. So that's why that means we need to orchestrate these AI agents in a way that that is consistent with our preferences. But in engineering settings or these computer scientist settings, they just try to do a better job in some tasks like coding. But now we want to do alignment, which means we want to harness agents in a way that its behavior is, or their behaviors are consistent in a distributional fashion as humans. Okay, so with this idea, we would like to, we will propose three systems to compare. The first is baseline. In this setting, we only provide the game instructions. Okay, what do I mean by game instructions? Let me just show you. Okay, here is the original paper of Clement Debo. It's just like it's the same thing as the real human experiments, how people, I mean, the experimenter would tell the subjects what to do. Okay, I don't, it's a bit long, so you can think of it, I just give them the context. What does it mean by waiting cost, the true product value, consumer type, so on and so forth, and how to make decisions, how to calculate the utility, the payment, as well as a calculator basically to help the human subjects to know how to do the calculation. So this is what I mean by the game instruction. And then, so then we just we then one step further is that we provide the AI agents the context formation, which means some specific areas that a human would look into or would more or less pay attention to in a real setting, because so if we don't really instruct some very much details of a context to LLMs, then LM would be just assume that we're just a random draw from the entire human society or something like that. Then all the specific context is kind of kind of a random draw as an input, so that the actual understanding of the context may be substantially different from what uh, what a real human would face. Okay, again, let me give you some idea what is our how do we do the context. So basically we would give them some more detailed understanding of this context, so that it's indeed something that a natural human would infer without really being instructed, but LLM somehow they would not really understand it in very detail, and they would just misunderstand it to a large extent. Okay, okay, like these things, or in the most or in sometimes we can think of it as a kind of attention, leveraging the attention mechanism of transformers, which are the foundations of LLMs, so that we instruct LLMs to somehow pay attention to these areas. Okay, let me go back to the slides. And finally, we just go one step further. That is, not only in game instructions as well as context formation things, we also instruct or harness AI agents how to really navigate this context. Okay, basically, we guide the reasoning within the representation of the context. Here, in our context, what do we mean? Okay, let me give you an example. By the way, these navigation strategies or the reasoning approaches, we will need to devise them into different ways, and we will train the weights of different reasoning paths. So like here, so basically we just instruct one type of consumers. That is, you rely only on weekly comparing benefits, and also you tend to avoid risky options, and also you give little consideration to behaviors, so on and so forth. So this is, and this actually corresponds to three areas or three types, okay, three human decision-making types that I will elaborate, and also to give you a sense of how we train the exact type distribution shortly. Okay, so this is our framework, or actually a system design. So as I said, we need to do some calibration of the harness navigation types. So basically, the idea is coming from Manning and Horton's earlier works this year, in the sense that basically, for specific human, they may follow different paradigms or different decision-making reasoning in the same context. As I just said, some people may actually be very rational, so they will compute the expected payoff. But for some others, probably, okay, it's just a simple lunch. I don't really want to burn my head. Okay, so then they will just use a very rough heuristic argument to make the decision. And also, some of the consumers, they may realize that wait time could actually be used to infer quality, but sometimes, okay, they just wait time is just a congestion for them. So that's another type. And finally, some of the users, when facing uncertainty, they would just take a very, risk-averse approach. Like, okay, there is some uncertainty in the realized quality of the product, I just leave. Or some of them are very risk-taking, or sometimes innovation-seeking, something like that. So they would, oh, there's a new restaurant. Okay, I will have a try at least at the very beginning. So basically, different consumers may have different preferences or different behavioral patterns along these three dimensions. So, but we don't know a priori what could be the actual setting, or in practice what would be the distribution. So the reason we do it is to, okay, how about we just enumerate all possibilities and let data speaks for itself, using the training, using a machine learning pipeline to train it. Okay, so specifically we just this is 2 to the power of 3 in total 8 different navigation paths, then we just, just that's why we have 8 different navigation possibilities. And then we use the real human data, the output. That means each consumer, whether he or she would like to purchase or not. And then we just use another loss function. Like here is cross entropy because it's binary decision. And then to minimize the in-sample loss of the AI agents, I'm sorry, to minimize the AI agents, the distribution, the entire populations, training populations, cross entropy of the agent's decision and human decisions. Okay, and this is the trained weights. Okay, but this weight itself is not that important. It just represents for this population, what is the behavioral pattern, composite of the entire population. Okay, so some results I would like to share. So first of all, in a baseline setting, that means we just give the same game instruction as humans, then both hypotheses would fail. Basically, yeah, because it's going, the AIs don't understand the context, and AIs may really take a different reasoning path as humans. If we only do a good job in context formation or representation of the context setting, still not sufficient because different people would have different reasoning approaches, different reasoning paths to navigate through that context. However, with both approaches, we provide the necessary representation, plus we train the population composition of the different type of users, then it could actually successfully replicate the theoretical predictions. Sorry. And indeed, we do some mechanism validation, which means we take a look at the chain of thoughts, which somehow we find that indeed humans, AI agents indeed think like more and more like humans as we move from baseline to context formation and context, as well as our entire framework. So here's another question. So we use the same distribution, original distribution of 50% of users are uninformed, first 50% of users are informed. Is there any kind of leakage or training and testing overlap or contamination issue? So we do out of sample test, which means we use the setting of 50% of the users are consumers as a training data, informed consumers, excuse me, and we validate or evaluate this outcome of the resulting agent in Q05, which means only 5% of the users or 5% of consumers are indeed what we call it the real who are informed. But does it really work? So if our framework actually could actually generalize to unseen conditions, we would see the alignment with human data. So then what we find is that okay, the similar pattern holds. So the baseline approach, the both hypothesis could not be replicated. If we only have context representation, still doesn't work. Whereas if we have everything, then it's quite successful. The hypotheses are successfully replicated. By the way, so the Q05 setting, the data is also recorded, or it's also open sourced by Debo and Debo's original paper. That's why we could do this test. But there's still some concern from the reviewers we face. That is, they say, oh, is it because the LLMs have memorized the results regardless of Q50 or Q0? Okay. Yeah, okay, fair concern. So which actually is, if you do similar research, then most likely your reviewers will ask you this question because it's a question that is always legitimate. Okay, although it doesn't make sense, but it's legitimate. Okay, I will let you know why it doesn't make sense later. Okay, but anyway, so basically, yeah, it's possible. GPT, Cloud, DeepSeek, Qwin, they all have, I mean, they may memorize these things. So we propose to introduce a new design which decomposes the waiting time into queuing time, which is generated by prior orders, and shipping time, which is randomly assigned. So what does it mean? Thinking of it as, let's say, a new product that is distributed by Alibaba, let's say Taobao or Tmall, but the capacity is constrained. Yeah, and so that you just like a memory, for example. Now you want to buy memory, you are going to face congestion. Okay, in this setting. So, but because it's an e-commerce setting, so beyond the queuing, you still have another issue that is shipping time. Okay, which is like if you are in, let's say, Shanghai or Hangzhou, then your shipping time is within 1 day. But if you are located in, let's say, Xinjiang, then probably it's 3 days. So basically, depending on where you are, the shipping time is different. But this shipping time is purely your waiting cost. You could not really use it to infer the quality. Okay, so basically with this, then what we could really predict is that, okay, if in this setting, then if it's still Q00, which means there's no informed consumer in this setting, then whether your waiting time is purely queue-based, so you don't need the shipping time, you don't have shipping time, or it's 1-1, so one shipping time, one is the queuing time. So in this case, we should observe very similar outcomes. And indeed, we tested, okay, it's very similar. And plus, so how about if it's, uh, yeah, so that's the thing. However, if that said, if it's Q50 setting, then in this setting, then we could observe a significant difference because between your that means if your waiting time is all from queuing, comparative with if your waiting time is some from queuing, some from the shipping, then in this setting, that means you could infer a better quality in this setting. Whereas if it's only the if it's only uninformed consumers, then both of them are the same. So basically, yeah, as we can see here that, so basically Q00 versus in these two settings, so the total waiting time is the same. Then these two, the yellow bars, they are similar. Whereas if it's queuing time, there is a queuing time difference. But the shipping time, yeah, the same total waiting time, but queuing time is longer, then the purchasing probability is higher if we know there are some consumers who actually are informed. So basically, yeah, this somehow, at least theoretically, this is out of sample out of sample tests suggests that our framework somehow works, but it's not complete yet because we are still in the middle of running an online experiments. So to demonstrate that this is indeed the human behavior. So basically, we derive these properties from mathematical models, but do humans follow mathematical models? In most cases, the answer is no. So we want to see if such predictions are indeed the real human behaviors. But yeah, I mean, if I give this talk two weeks later, probably I can show you the human results. But for now, we don't know. but I do believe this should be the case. Okay. So this is another thing. And another perspective is, okay, is our model really constrained to this single setting? The answer is still no. So we still apply our model, our framework, our system to another two cases. The first one is the notorious 1120 morning request game, and the other is dictator game. I don't want to go into details, but basically these are very important ways of testing human rationality and as well as altruism. Basically, what we find is that using the baseline approach, compare with a baseline and using context formation only, if we use our entire framework, the error, out of sample error between the human subjects and the AI agents would decrease significantly. So the error will go down a lot. So basically means that this approach somehow is indeed working in different contexts. Okay, so all in all, what I want to say is that we propose this framework, which you could indeed replicate some results based on human behaviors and could generalize to unseen conditions. Okay, yeah, there is another critique we face from different contexts. Basically, a lot of people say, "Oh, these are some simple and quote-unquote well-studied ideas here and there in the literature, blah blah blah. There's no innovation." So be careful if you want to do similar research. Okay, yeah. Anyway, your results are not novel is always a good reason a legitimate reason to reject any paper. Yeah. But anyway, this is just yeah. So I will acknowledge that every single piece is not that cool novel, but pasting them together and rigorously demonstrating the system as a whole works. Yeah, let's say whether they will. Yeah, this is kind of something that contains enough novelty at the end. But at a high level, just share with you some of the critiques we face during the past few months, so that yeah, if you do similar research, yeah, you could somehow you need to defend yourself along these dimensions as well. Okay. Okay, spent too much time on the first part of the talk, but now I would like to switch gears towards the second part of it, that is the post-hoc calibration to enhance causal estimation with AI-generated labels. Okay, so at the end, so basically in a lot of settings, we use A/B testing to draw causal relationships between an intervention. Like yeah, but the issue is that in A/B testing is field experiments sometimes expensive, sometimes no, sometimes unethical. But LLMs or AI agents could instead somehow provide us these labels, okay, that could replicate the human experimental results. But the problem is that we don't know, or in a lot of cases, the LM's output has low quality. The quality is not as good as human labels. Plus that there will maybe some systematic bias. Okay. So basically, the key question is, can we combine the credibility of real data and the scale of AI-generated data to do a better causal inference task for an A/B testing or experiment? Okay, so if we naively use LLM generated labels, here I give you an example. So basically, our data set has roughly 200,000 customers. And so basically, the treatment group is you have a promotional show message. Control group is no promotional message. And roughly the difference, the gap or the lift, average lift is about 3.3% conversion rate change. However, let's say if we use if we just randomly sample 50 true outcomes, then the AT estimate will be roughly 40%, and the estimation MAPE is about 1/3. Whereas if we directly use LLM to still generate 200,000 LLM predictions, then the AT estimate will become 11%. And the MAPE is roughly 230, which means, yeah, although LM could easily generate the labels for us, but the estimation result is just, I mean, off the chart, and it's completely unreliable. So then the question is, okay, can we do a better job than both of them? So the answer is yes. And the entire framework contains these three parts. The first part is that we need to calibrate the bias, which means we need to use a small gold standard human experimental data as the ground truth to actually debias or calibrate the LM generated sample. And then we need to we then follow the standard causal inference literature to and to incorporate such calibrations into such frameworks, and then to which could provide us a valid inference. And then both approaches could also help us to make better decisions as well from a policy learning perspective. Okay, let's see the setting. The problem. So we have a primary data set, which I call it DP, which contains the features, covariates, the treatment assignment, the true label from humans, and the AI-generated label. So this ZI from XI and TI, but does not come from YI. So this is the primary data, which has everything we need. Auxiliary data only has the feature, the treatment assignment, but not the true label. But we could, of course, use X and T to generate the AI generated label. So, of course, the sample size of the auxiliary data is, orders of magnitude higher than the sample size of the true data or the primary data. Okay, so yeah, what we would do for the LLM generation is that we just we probably do some few short prompting with representative examples and provide the covariates and treatment, and then ask an LLM to generate a label. Okay, and this could be general. Okay, it could be anything that could give you a reasonably good property, reasonably accurate predictions or outcome. Okay. Of course, there's a lot of issues like the bias of the model, hallucination, and also probably our prompting technique is not as good, or there may be some distributional shift, and yeah, a lot of other things that LLM per se cannot capture. So that's why we need to do label calibration. So the idea is like this. So basically, we train a model, a small model, which maps the feature X, the treatment assignment T, and the AI-generated label Z back to the true label Y. In our case, it's whether the consumer is conversion or not. And then we will use this calibration mapping as a way to regenerate the pseudo or auxiliary label from the LLM generated label, like X, T, and Z. We map it back to Y tilde. So Y tilde, of course, is not the same as Y itself, but could serve as a proxy for Y. Okay, so for this, then we could then follow the standard estimation and inference approach to do this task, like using, let's say, difference in mean, ordinary least square, or linear regression, inverse propensity weighting, double machine learning, so on and so forth. Okay, that means we do not use the real Y because we don't have it in the auxiliary data, but we use a calibrated Y in these estimation inference methods, and then follow the same paradigm, which could generate us the estimation. And we also could do policy learning, which means we could learn, let's say in this setting, we could learn for each consumer whether we could send him or her a text message for the promotion, and how could we do a personalized promotion so that could maximize the total welfare of the entire platform. And we can actually derive some, we can use only the primary data, we can use auxiliary data only, or we can combine both of them. And with that, we could actually develop the so-called regret bound, which means how much away are we from the true optimal policy or personalized policy. Okay. But here we need to use, in this setting, because we need to do individualized policy, we need to use double machine learning, which could cater to individualization in this setting. Okay, so this is the general framework. I don't go into details because I know probably most of the audience are not in this technical background, so I'm just giving you the high-level idea. The context looks like this. So we we just found a data set of a Russian e-commerce. It's called X5 Retail Hero dataset. This dataset has 15 covariates, and it also it's a experimental data, which is very rare. Okay, public available large-scale field experiment data. So it has treatment group, which means short message is received, a control group, which means there's no short message promotion. And the outcome we care about is whether there's a conversion, which means whether this consumer would like to purchase the product or not. Okay, it's a binary outcome. So we compare our approach with this benchmarks, but it's incomplete. I just show you some clinical ones like difference in mean. This is our framework, difference in mean, ordinary least square, IPW, and DML. So here, the purple bar, this one is our approach. And this one, PPI, prediction powered inference, developed by Michael Jordan. It's a science paper, which cannot be directly incorporated. It's a different idea. So basically, what we want to argue is that our approach has a much, I mean, the MAPE, the mean absolute error, is substantially smaller. This is precisely because we do calibration and we leverage both the calibration, the power of calibration, and the power of this statistical framework to do causal inference. So here I compare both the primary ratio, which means 1% of the data has true label, and 99% doesn't have, or 2% has true label, and 50% does not have. So basically, if this primary ratio goes to 1, that means of course we should use the primary data to do this task. We don't need to use the AI generated labels. Another perspective is let's just set aside the same MAPE that is the estimation error, and at different 30% MAPE or 50% MAPE, let's compare the required sample size. And as you can see, regardless of what kind of underlying model we need, excuse me. We require substantially fewer data with human labels, okay, at the same estimation quality. Another perspective is this is the so-called policy learning perspective. We use optimality ratio as the benchmark, as a metric, which means regardless of what method we use, we don't do anything, compared with Oracle method, which means it's purely fully personalized, and it's perfect. It just assigns the best approach for every single user in the experiments, and compared with we don't do anything. So this is the Oracle. So basically, it's how much of the total value we can gain from the fully personalized policy compared to, we compare with this Oracle, how much gain we can have using our proposed policy learning method. So basically, what I want to argue here is that our approach indeed does a much better job than those benchmarks, okay, which don't use calibration, and or we just use a simple, we just leverage simple ATE. That means we just treat all. Okay, so either way, we are doing a better job than those benchmarks. Okay. Okay, so with this, I think I could like to give you a short summary. Okay, so basically, as we zoom out a little bit, so what we're trying to address here is that, so AI is very powerful, potentially more powerful in social science research. We could use it to simulate real human behaviors and to understand how humans would do under a lot of interventions that we cannot run experiments. So we can do such simulation, but such simulated data is biased, so that we could do a pre-hoc calibration using context formation and harness navigation approaches. but we need to use limited human data to do the calibration. Or we can do it a post-hoc calibration in causal inference, which means we could use LLMs to predict the labels, but these labels are biased. So we use a calibration plus the causal machine learning frameworks, then we could still obtain or recover the causal estimates from the the true human estimates. Okay. So I believe AI per se is at least as of now, it's not a replacement for theory or experiments, but a calibrated complement in the empirical pipeline for social science research and business research in particular. So with this, I would also like to, before I conclude, sorry, let me see. Yeah, here. So because just now, here, okay, let me change. Yeah, just now Professor Liang says I have a PhD course, so yeah, you are welcome to join. So I open source everything on GitHub, and this is a 2026 version, and also you can go to the 2025, 2024 versions. And I also gave another one at Shanghai Jiao Tong University as well. So, and also these recordings are also available here, and some notes. Both Markdown, which you can use AI to read, or you can read on your own, which are PDF versions. So yeah, it's very AI native. Yeah, let me put the uh let me see everyone. Yeah, so I put the GitHub site here, so you are welcome to see, and also you are also very welcome to join the class next year as well. And everything will be totally different as AI is evolving so fast. So with this, I would like to conclude, but also, yeah, you can. Yeah, I also put my WeChat in the chat box in case you are interested in discuss more with me. Yeah, so let me go back to the slides. Yeah, if you have any questions, so I'm more than happy to discuss here. Thank you very much. Yeah.
Yeah, thank you very much, Professor Zhang. So, thanks for the very inspiring talk, and it's a very timely one. So, I encourage you, all the students to go through at least the syllabus so that you will see how much effort actually Professor Zhang that made that for the course syllabus that is changed every year a lot. And I guess that it also reflects how quickly that is the landscape, so the whole AI area that evolved in the past few years. So in fact, I have a lot of questions, but before that, I guess that also our audience have a lot of questions too. So you go first. You can just yes to unmute to ask or post questions in the chat box.
Hi, may I ask a question?
Yeah.
This is Yingyi. So yeah, Phil, I find your talk fascinating, really eye-opening. So I have a question regarding the first half of your talk about synthetic decision making. So yeah, can you hear me?
Yeah, of course.
Yeah. So it seems like that you are taking advantage of implicit inference, the implicit inference that people might be using. In this case, is how the weight light infer the quality of the restaurant, correct? So
yes,
yeah,
in this case, yeah.
Yeah, in this case, and then so this implicit inference seems to run against the regular utility model, which is the time cost. But what
Mhm.
if the implicit inference go, not it's not augment or go against the regular utility
Mhm.
model.
Mhm.
If it's in the same direction, it seems like
Mhm.
it's entangled. It's hard
Uh-huh.
to differentiate.
Mhm.
So actually the framework would apply to implicit inference that is against or opposite to the regular utility model, correct?
Okay. I would say it goes beyond or more general than what you just described. In a sense that so basically here I will call it in this way. So here in this example, there is a trade-off or the
Mm-hmm.
competing forces like a congestion
Right,
waiting
right.
time versus
Mm-hmm.
the quality inference value of wait time. So
Right.
that's why in this setting I would say it's a good thing to investigate because it's trade-off, and plus, then we could actually develop such a trying to this hypothesis from both theory and a lot of other things. But if every force goes to the same direction, then of course the hypothesis probably may be much simpler. But still, we may face a lot of I mean the different consumer types like this one.
Mm-hmm.
So
I see. Yeah.
basically, yeah, they may go to the same direction. It's okay.
Mm-hmm. Mm-hmm.
But the point is, we are not trying to test which force is stronger, which force is weaker. This is too detailed, at least at this stage of the whole I mean the whole agenda. But now we are saying, okay, we don't know how people behave in these dimensions.
Mm-hmm.
Let's just do it in a more data-driven way so that we know probably these factors may jump in. But
Mm-hmm.
which factors should we consider is a bigger question. Actually, I don't have a good answer now. Yeah, probably next year we discuss again. I can give you a better answer. But currently, it's just some related, I call it related or relevant possibilities that could characterize the human decision reasoning in this setting. So basically, we characterize these three. It seems to work. But is this the best three, or should we have four? The answer is I don't know. But at least these three seem to work well. So yeah, that is whether the consumer would like to compute the payoff, would the consumer like to infer quality,
Mm-hmm.
and would the consumer be very risk-taking or it's just very risk-averse? Yeah. So at least in this setting, these dimensions of decision-making rationale at least matters and would work in that setting. But they may or may not contribute in the same way or have a trade-off in the exact context. Yeah.
Yeah.
That's what I have. Yeah.
Yeah, I have a follow-up
Mhm.
comment.
Mhm.
So in that case, it seems to me, as a social psychologist, actually, I'm trying to, bridge what you are saying with the social psychology approaches. I think what you talk about here is that the AI can be a good tool for testing, for example, the lay uh, inference, because oftentimes in social psychology we don't know, and many of the social psychological theories are
Uh,
about how people
uh,
make
uh,
implicit inferences. So I think the context formation would make the AI as a very good tool to test the implicit inference, and then the honest navigation would be a good tool to test individual differences. So that's
I see.
again another very
I see.
important
I see. Interesting
search
perspective.
approach. Yeah.
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 Thanks for the
So that's
comment.
my comments. Yeah.
Yeah,
Very
thank you.
fascinating. Fascinating. We can talk more later.
Yeah.
Yeah.
Yeah,
I'll
sure.
follow up with you. Thank you.
Sure. Thanks. Yeah. Yeah, but yeah, that's a good yeah. If somehow such a paradigm is more acceptable, and also or we could build more connections with social science theory, then yeah, there may be some way to use not only to test the behaviors, but also to test the underlying latent
Right.
rationale and representations. Yeah,
Right.
some
Right.
purpose. Yeah.
Right. Yeah.
Yeah.
Fascinating. Thank you.
Yeah, thanks.
Thank you, Professor Hong's questions, because you just mentioned the implicit responses. I see a question from Shannon, our PhD student. Actually, he's working on some similar project. Okay, Shannon. Hi, Shannon. He just typed the question, but anyway,
I can take a look. Sorry, where
no, no,
you?
no, no, no. They just type the
Oh,
Q.
Okay.
okay,
Yeah, can you hear me?
okay.
Can you hear me?
Yes. Yeah, go
Oh, yeah.
ahead.
Yeah,
Thank you for your sharing, Professor Zhang. Yeah. My question is quite simple. Yeah. I guess you did a lot of work and based on the standard large language model. So I just wondering, did you ever compare your result with the fine-tuned large language models? Like you can put the ground truth data into the large language model to get better performance. And some companies have provided the interface because you have to do a lot of collaboration work. So I guess if the fine-tuning model can have a better performance, it is a most cost-effective way. So I just wondering the result. Yeah.
it's a good question. I would say my intuition is most likely no. But of course, I don't do a very comprehensive study because if you talk about fine-tuning, then that is first of all, a lot of um, so there are multiple ways of doing that. Of course, the best way is, of course, if you have 10,000 GPUs, then you deploy a model locally, and let's say GLM 5.2 or Kimi 3, right? Then of course we can test everything, and I believe this is going to work, but it's too costly. Then a compromise version is either you deploy a very small scale, let's say 10, I mean, at a magnitude of dozens of billion or to the most, or sometimes you are not rich enough, then you can go just, let's say, a few billion, 3B, 7B, something, chain this scale. For these models, yeah, then you could use then for some tasks, I believe you can you can you can find a lot of to and then to find then you to either use supervised fine tuning or reinforcement learning with verifiable rewards. And I believe this is going to do a reasonably good job. But whether it could really achieve the alignment at the level of, let's say, the state of the art, or at least the models that could size exceeds the level of I mean a certain level that an individual social science researcher could actually handle. I highly doubt. And the reason why I don't do it is because indeed, for most of the interesting social science research questions, we don't have that large scale data to actually to actually do the testing at the end so that we know the alignment is good is good or not, and to do the training at the very beginning. So this is a very challenging task indeed. If some of you who are in the audience could have that much money to do that task, I would be very, to collect the data, to run large scale experiments, and to use that experimental data for fine-tuning large language models that and also of course to host these large language models. Yeah, I would say it's yeah. Yeah, I would very appreciate such effort, and I would definitely work with you to along this line. But it's challenging, and but if we let's say for this data set I have, which I show you, the magnitude is several hundreds. At this magnitude, if you want to fine tune something, it's just I don't believe this is the case. I don't believe this is going to work that well. And finally, the third approach is that like some places like OpenAI, they give us a service that is to fine tune. So you provide some data to them, and they just use their fine tuning pipeline to help you fine tune. And then, but this is a more black box. You cannot have much control, and a lot of things you cannot really. It's hard to customize, and some people actually are using similar approach and report the results in some papers that I know of. The results are not encouraging, at least suggesting at this data scale with the, I mean, vanilla version of the fine-tuning service of these large language model providers like OpenAI, probably it's not going to work that well. Yeah, so basically I would say, yeah, if you have enough money, I believe fine-tuning and reinforcement learning with verifiable reward would do a reasonably good job. But I think that's too costly. But within our cost constraint, the showed evidence or signal that I receive as of now cannot really do well for the questions or the inference tasks that I show here. Yeah, that's what I
Thank
know.
you for this insights. Yeah.
Okay, next from a few questions from Xiaoqiang, also our PhD student. It typed it in the chat box. And Xiaoqiang, can you ask directly, or are you still in the hospital?
Of course. Can you hear me? Professor?
Yes.
Yeah. Thank you for insight for sharing, and I'm quite interested in the calibration of using large language models to research, and I have several questions, and I also put it in the chat box. Firstly, in terms of the first method of pre-hoc method, I wonder, for my understanding, I think the navigation prompts work well in this method, and I think it's a kind of using user preferences. Do you think the navigation prompts represent all types of human subjects, or do we
good
need
question.
to?
Okay.
Yeah.
Let me answer it. One. The answer is indeed we don't know what to put here. Actually, yeah, just we could get some inspirations from the literature, from social science or whatever, psychology or other type of research. But I mean, there's no way we can say we enumerate everything. So yeah, but how do we choose or select? We could do it in a machine learning driven or data driven way of, let's say, using some loss function like auto research type of things to do that. But how credible it is, actually, I don't have a good answer. So basically, I would call it more art than science. And indeed, this is another question that you may face doing this type of research in the review process. The reviewers will ask you, okay, yeah, I mean, how can I get the quote unquote right theory in this setting? I mean, yeah, I don't have a good answer. Of course, you can argue, okay, literature, similar approaches, yeah, similar settings here and there. But of course, you can not enumerate everything, right? Of course, and yeah. So.
Yeah, I agree. And the second question is about another line of using large language models. As we can see, some scholars may want to use demographic features to stimulate human samples. And I think the basic idea is that once we can replicate human samples with demographic features, we can also get the accurate inferences from those silicon samples. Do you think it is useful or reasonable in specific context using demographic features, or how can we see the differences between silicon samples using
Mhm.
demographic features
Sure.
and navigation prompts?
Sure. A good question. My answer is actually clear for this one. If you can have the demographics, this will help you. The problem is we don't for this because we need to do calibration so that the uh, then that means the data it is constrained by the data we have, like the real human data here, right? We need to train the minimizer. We need to train this the loss. We need to minimize this loss. So if we have demographics or persona data, of course we should do it. We should include it. That will help from various different research has already showed that. Of course, we should. But the problem is, it's not always the case that we have such luxury. Yeah.
Yeah, I see. Thank you. And also, the third question is about the second method, method. And I thought there is a critical index called primary ratio, right? I found that as the error MAPE is getting smaller with
Yeah.
its increase.
Uh-huh.
I wonder how we can choose optimal primary ratio, or is there
I
any
see.
rules of that? Yeah.
Sure. Thanks. So, probably I don't get it very to the super clear level because the primary ratio means the amount of data. Let me see this figure here that has a true label. So if we have the true label, then of course the quality is going to be better if if we fix the total number of data observations. If the primary data gets larger and larger, the proportion gets larger and larger, it should be expected that the quality of the estimation gets better and better because now that means we have more ground truth data. So that's its thing. So basically, if this one goes to 1, then that's the best we can have. Yeah, that's the idea here. Indeed, that MAPE is compared against the average treatment effect if we have a lot of primary data. Yeah. So that's the
So
that's the
do
case.
you mean we should collect much more true labels as we can?
If we have, the answer is yes, right? If we really can, we should, because that will help us better do a better job in calibration. But the problem is true labels take a long, and sometimes it's unethical to collect. Yeah.
Yeah, I think, thank you. And the last question is more general. In terms of the calibration, how can we combine the pre-hoc and the post-hoc ways? Should always compare both of them?
Good question. So probably we can discuss 1 year later because we just both are necessary or could help, but which one is, of course we need to further research to determine in what situation the pre-hoc approach is more important than the post-hoc, and in which context is the other way around. Of course, more investigations we need, and of course, if we combine them, that we could expect a better result. But in what way and how these things synergize, of course, should be left as future research.
Thank you very much.
Okay, thank you. Thanks for the questions.
Okay, probably the next question from Ouyang Rongxin from US.
Yeah, thank you, Professor, both professors, I would say, for this seminar and this great talk. So my question would be more practical, and it's more related to the error part of the second study. Let's say that if you are talking about measurement error by either human beings or large language models, we have at least two types of it. The first one is some like something like a systematic error, right? That we are trying to calibrate here. And second one is about random error. Well, in traditional survey study or experiments, I think both of them have like a huge abundant like different vans of theories. But in the context of large language models, I can see at least two things that I would ask you for any recommendation or comments on this kind of things. Let's say we have at least two new things here. The first one is about systematic error brought by like the model drifts. For example, if Queen modifies their model, how can we replicate those kind of study? And second thing is about random error here. So, well, we can assume that they follow normal distribution about the random error, but the practical issue is that the inference engine of models are changing or like technically they're running in different ways. For example, they may use different prefill technologies. They may slightly change the parallelization or everything else. Should we still assume that we can use a normal distribution to reduce this kind of random error? So how can we deal with the first one, the model drift, and second one, the random error like introduced by unknown technological changes? Thank you so much.
Okay, thanks. Okay, so my understanding is that because large language model itself is what I call it a random, it's a next token generator, randomized next token generator. So basically that means so random, quote unquote, random error or randomness, which shall we call it an error, is debatable. So it's it is there as always, and yeah, because of that, and it's on at its outcome. Here we're talking about outcome. So basically, the standard statistical theory will tell us that if it's really random error, then it's something that will be propagated through the statistical pipeline, and which basically means that a larger confidence interval, which I think should be more or less okay in this setting. I will say it in this way, as long as you generate sufficiently more data as well as a model becomes stronger and stronger. But so here, that means here what we are doing here is more on the quote unquote systematic drift. Either it's because of model or it's because of a lot of harness techniques used by these companies, or it's just because of some alignment choices. Okay, these things. So regardless, or sometimes because of sampling. So LLM itself is it first samples a human feature and then samples the outcome, so on and so forth. And so this so for here, what our approach is actually quite straightforward. So basically, that means we just try to use a small LLM, not really LLM, a small machine learning model, F, that could somehow predict this error, basically. I would call it, or calibrate or reverse this this error path to the extent possible. So here I don't show you the technical details, but here basically what we require is that this estimation here, this one. So basically f hat, this approximation, we need some statistical property of this approximation. That means f hat should converge to f star sufficiently fast. And only in this setting can we actually achieve the right estimation and inference result. Because that's this is, as you can imagine. So basically, in terms of systematic error, basically what we are assuming that indeed we can use a machine learning approach to fully recover this error. Okay, with sufficiently fast convergence rate. So that's basically, in essence, we're using another machine learning to recover it. That's our approach. But whether using the standard measurement error techniques in the literature to capture that, I would say, at least I don't see a lot of promising results so far, to my best knowledge. So I really the Santio Professor Santio, I cannot pronounce his full last name, from Harvard, working on econometrics and machine learning, Harvard Econ, actually wrote a recent, I mean, last year actually wrote a paper about this measurement error problems. However, I have replicated his results, but not very successfully. So basically, so that's basically because whether you are generating X, that means the features, the covariates, or you are generating a treatment, or you are generating the Y, the labels, then there are always measurement errors, systematic ones. And if we have them, and then it jumps into, I'm not Y, Z, I'm sorry. So, and then he proposed some approaches to actually to quantify it and address it. But the results are not very promising. So that's why later myself and a few other scholars try to use a more, I would say, theory agnostic, but more data-driven way of directly calibrated using machine learning. So, but whether this is the final, but this approach of course requires some assumptions in terms of convergence rate. So that's a cost we pay. That's my understanding for now. But if you have any better ideas, we can discuss more offline.
Yeah,
Thank you.
Prof. Thank you for your answer. I think it's a great answer. May I ask like a small follow-up question about the first part of my question? So I was thinking about a more practical yet also concerning scenario in which we may want to use some machine learning model to generate some labels. However, the model itself might not be like stable at every time point. For example, if we spend 2 days to predict the same question, the first day is DeepSeek V3. However, we cannot access to DeepSeek V3 in like tomorrow. Although they expose the same API or the model ID from the service perspective, this kind of like drift in the model may actually bias our calibration method because the features we learned from those kind of training set is biased.
Okay.
So how could you deal with this
sure.
thing in your pipeline or something like that? Yeah.
Sure. This is a practical question, so I have a practical answer. So please develop an AI agent to scrap the breaking news from X from so that you will know a lot of such rumors beforehand. Then you will that's my practical answer. Then
Thank you so
to
much.
avoid that.
Data rates are really need smart street smart. Yeah. Thanks.
Okay. Thank you all for the questions, and also thank you, Professor Zhang, again for the inspiring talk. Because the time constraint that we have to swap here, but you can always reach Professor Zhang through email, through WeChat, and also through Xiaohongshu. Okay, please follow him. Okay, thank you again, Professor Zhang. Yeah. Now
Thank
we
you.
have more to discuss offline later. Yeah.
Okay. Thank you very much. Feel free to reach out if you have any further questions. Bye-bye.
Okay, bye bye.